Okay, welcome back, students of chemistry. This is a short recording on how to solve gas law problems using using the relationships that you learned in your gas relationships lab. So I want you to consider what you learned in your gas relationships lab before you start the problems. You learned that pressure and volume, oops, that pressure and volume are directly related. If pressure goes up, or inversely related, as volume goes up, pressure goes down, or as volume goes down, pressure goes up. You learned that an increase in temperature will cause an increase in pressure. That's a direct relationship as well. And you learned that increasing the amount of a gas will also increase the pressure of the gas. So when we're doing these problems, what we're going to do is consider those relationships that you saw in your laboratory. One thing that you didn't get a look at was the relationship between the temperature of the gas and the volume of the gas. But if you understand that temperature is really measuring the motion of the particles, the more the particles move, of course, the more they're going to collide with their container, and therefore the higher pressure. And if you have a volume that is not fixed, meaning it's not a metal can or something like that, a volume that can expand, whenever those particles collide with the side of the container, they're going to cause that container to expand. So temperature and volume are also directly related. Increase in volume increases the temperature. And then the same with the amount. The more gas you have, the larger the volume of the gas is going to be. So the more particles of gas, the larger the volume. So these are the relationships that you're going to need to think through as you are doing these problems. There's only one that's inverse. Ladies and gentlemen, which one of these is not like the others? It's this one, pressure and volume. So if you know that pressure and volume are inversely related, and then just know that everything else is direct, that's really kind of all the work that you need to do on that. Okay, let me show you how to solve these problems. So what I'm doing with this PVNT chart, and you don't have to always use it, we'll use it for now, and then you can discard it as you're going, is I want you to write the initial conditions of the gas, and then what are the final conditions of the gas, and what changes under effect here. I want you to kind of put what changes are occurring. So what we have here is 150 milliliters of a gas. Milliliters is a volume, so we'll put that under volume, 150.0 milliliters. And it says, what is the volume when? So we're solving for the new volume. The temperature is going from 25 degrees Celsius, and please remember that we cannot leave that in the Celsius scale. We have to convert that to Kelvin. 25 degrees Celsius is increased to 50 degrees Celsius. Oops, I did not mean to write that there. So 25 degrees Celsius, when we add 273, is going to give us 298.0 Kelvin. And then the final temperature is 50 degrees Celsius. 50 plus 273 is 323.0 Kelvin. Notice that I'm not using that conversion as my significant figure determination. We're going to use our measurement with the 0.0 and keep that. Okay, so if we consider what's happening, what I want you to do is think through the changes. It says pressure and the amount of the gas are held constant. What's happening to the temperature? The temperature is increasing. So you need to think about what happens to volume when temperature is increasing. Pressure and volume are the only ones that are inverse, which means temperature and volume must be direct. So if the temperature increases, that means that the volume is going to increase. So what we're going to do is take our original volume, 150 milliliters, and we're going to multiply it by a fraction of the temperature. So this is going to be a temperature fraction. And we're going to make a fraction of these two temperatures such that it results in a larger volume. So if you consider the two fractions we could use 298.0 over 323.0, or we could use the fraction 323.0 over 298.0. And if you consider that this fraction is a fraction that is less than 1, if we multiply 150 by a fraction that is less than 1, we know that that's going to make that number go down. This fraction 323 over 298 is a fraction that is greater than 1. So we know if we multiply 150 by that, it's going to get bigger. So that is the fraction that we will use. 323.0 Kelvin over the 298.0 Kelvin. And in doing that, our units Kelvin will cancel out, and we keep our unit milliliter. We get a volume of 162, 4 significant digits, 162.6 milliliters as the new volume. So that's how we're going to solve these problems. We're just going to think about it and multiply it by a fraction of what is changing to figure out what we're going to get. Let's do one more like this, and then we'll pause and do one that has two variables changing. So we've got the pressure in a bicycle tire is 98 kilopascals. They're telling us that's a pressure, so we'll put it here under the initial pressure. And that's at 25 degrees Celsius. We know that we cannot keep that in Celsius. We have to convert that to Kelvin. So 25 plus 273 is 298.0 Kelvin. We're taking that bicycle up a mountain where the temperature is now negative 5 degrees Celsius. Negative 5 minus plus 273 gives us a final temperature of 268.0 Kelvin. It says, what is the pressure in the tire? We're solving for the final pressure. So what we're not changing here is the volume of the tire, so maybe that's a pretty rigid tire, and the amount of the gas in the tire. The tire does not have a leak in it. So if we want to know what is the new pressure, we have to consider what's going to happen to the pressure when we change the temperature. We know that pressure and temperature are directly related, which means whatever the temperature does, the pressure is going to do also. So here the temperature is going from 298 to 268. The temperature is going down, which means the pressure inside the tire is also going to go down. So we're going to take our pressure, 98 kilopascals, and we're going to multiply that by a fraction of the temperature. So this is a temperature fraction, because that's the thing that's changing, right? In such a way that the pressure goes down. So we need a fraction that is less than 1. So if we want the pressure to go down, our fraction needs to be less than 1. So on top of the fraction is going to be the smaller number, 268.0 Kelvin. On the bottom of the fraction, 298.0 Kelvin. We can see that our units Kelvin cancel out, and we end up with a new pressure of 88.13 kilopascals. The joy of solving these problems this way is you know if you've done it right. As long as you know the relationship between pressure and temperature, you really can't get it wrong. Use a different fraction if you don't get a smaller pressure. Okay, so we're going to move on now just because I don't want the recording to be too long, to a problem that has more than one variable changing. Now these other problems you should do yourself. Okay, so here's a good one. This says we have a gas that is 250 centimeters cubed. That's 250 milliliters of gas. That is a volume. And it's at 25 degrees Celsius, which is 298 Kelvin. And it's at 730 millimeters of mercury pressure. The amount of the gas here is going to be held constant. So it's in a container where there are no leaks. It's been trapped. And it says, what is the new volume? So we're solving for the final volume of the gas. If this is changed to standard conditions. So you need to know the conditions of standard temperature and pressure. You probably remember standard pressure is 1 atmosphere, 760 millimeters of mercury, or 101.3 kilopascals. We're going to use the millimeters of mercury. So what we're saying is, hey, what's the volume of this gas at standard conditions? Standard pressure is 760, so that's going to be my final pressure. And standard temperature is 0 degrees Celsius. Expressed in Kelvin, of course, that is 273 Kelvin. That is standard temperature. So we're going from a temperature of 298 to a temperature of 273 Kelvin. And we're solving for volume. All you have to do is think of these individually. If we consider the relationship between pressure and temperature, I'm sorry, we're solving for volume. Between volume and temperature. We're going to take our new volume, or our first volume, 250 milliliters, and we want to multiply it by a fraction that matches what we know will happen. So when we consider temperature and volume, the temperature is going down. Volume and temperature are directly related, which means the volume is going to go down. So we're going to make a fraction that is smaller than 1, because we want the 250 number to get smaller. So we'll put the 273 kelvins on top. We'll put the 298 kelvins on the bottom. Kelvins cancel. And now we'll have a new volume that is smaller than our original volume. But we're not done, because the temperature is not the only thing that's changing. The pressure is also changing. So now we need to consider the relationship between pressure and volume. So we need another fraction. And we know that when pressure increases, like it's doing here, so our pressure is going up, we know that pressure and volume is the only inverse relationship that we have. All the others are direct. So if pressure goes up, the volume's going to have to go down. So here, our second fraction needs to be a fraction that's going to make the volume go down, which again means that we're going to need a fraction that is less than 1. So 730.0 millimeters of mercury over 760.0 millimeters of mercury. So basically what we're saying is, hey, both of these things are going to change the volume. Which one of them changes it more? And you guys, they don't always have to change them in the same way. Sometimes it might be that one of the factors makes the volume go up and the other factor makes the volume go down, and that's okay. It's, you know, the one that prevails will be the one with a greater change. So now we'll just do the math. 250 times 273 times 730. Divided by 298, divided by 760. And we get a new volume of 219.98, so it's really 220.0 millimeters of mercury cancel. That unit is milliliters. So this is how you solve gas law problems when you have repeating conditions. Now we're going to move to just one more problem, and that's going to be one where there are no repeating conditions. Okay, so here's a problem where there are no repeating conditions. All we're given is the amount of the gas expressed in moles, 1.20 moles. Please remember that that might be given to you in grams, and you know how to get grams from moles. You know how to get moles from grams if you know the substance. The temperature of that gas is 25 degrees Celsius, so that's 298.0 Kelvin. I'm keeping the 0.0 from there. And then the pressure of that gas is 760 millimeters of mercury. The question says, what is the volume of the balloon that the gas is in? So what we're going to do here, since we have no repeating conditions, is use our ideal gas law, PV equals nRT. We're solving for the variable volume. Volume is equal to nRT divided by P. And then we can plug in Chug algebraically. N stands for moles, so that's 1.20 moles of a gas. R is the universal gas constant, and that's something you want to put in your steel trap. So R here is 0.0821. Watch the unit, atmospheres times liters over moles times kelvins. The unit on the universal gas constant is a fractional unit. We'll multiply that by the temperature, 298.0 Kelvin. And then we'll divide all of that by the pressure. Now notice that the pressure in the universal gas constant is in atmospheres, and this pressure is in millimeters of mercury. So we're going to have to convert. This one happens to be standard pressure. However, I'll just show you the conversion. So 760 millimeters of mercury is what we have. We want to put that into atmospheres. So we know that our conversion factor is going to have standard pressure in millimeters of mercury on the bottom and standard temperature in atmospheres on the top. So that's going to give us 1. Let's see, we've got 5 significant digits. 1, 2, 3, 4, 5 atmospheres for our pressure. So our pressure then is 1 atmosphere with 5 significant digits. You can see which units cancel. There's a mole on top and a mole on the bottom, a Kelvin on top and a Kelvin on bottom, an atmosphere on top and an atmosphere on the bottom. So now that we know that our volume is expressed in liters, because that's the only unit that's left. And hey, that even tells us that we did our algebra correct. So if we chug it out in the calculator, I'm getting a volume of 29. Looking at 3 significant digits because of our moles, so 29.4 liters is the answer there. Okay, so you should finish the rest of the problems that are on that note sheet and then start working on your problem set.